All right, so let's go through the solution to homework 8.2, and I've done a little bit of work coming into the video based on the supplement that we recorded during the last video. I think I could probably set this up pretty quickly, and it wouldn't be too much of a hassle. So with this problem, you were given a couple of pieces of information. For starters, you were given the stiffness values of each of the 6 elements. So it was 4, 1, 5, 2, 10, and 8. So here are the 6 stiffness matrices for each of those elements, and I've just written those there. And we know that the system is going to be 5 by 5 because there are 1, 2, 3, 4, 5 joints, and each joint contains 1 degree of freedom. So if you want, you can kind of think of the system like this. And again, I know that this assignment, we're really not talking about coordinate transformation or rotation, so I know that maybe the angular orientation might have thrown you for a loop, but really what was critical with this assignment is just ensuring that you understand where each joint intersects and how it's assembled. So let's take the joint that you were given as the member that you were given as an example. So let's take a look at K3. So K3, here's the stiffness matrix, and you were given the member codes as 2, 4, 2, 4. So, and again, if you look at element number 3, we're talking about this element, it goes from 2 to 4. So that's where that comes from. So those terms, again, one by one, go there. And that's where they go inside the stiffness matrix as a whole. And so we just keep doing that for each element one to one. So let's see. Element number 1 goes 1 to 2. So that goes, so you can see from 1 to 2. So those terms go here. Okay, what about element number 2? Element number 2 goes from 3 to 4. So element number 2, 3, actually let's put element 3 to 4. So that goes there. So that's where that element goes inside the system matrix. Element number 4. Element number 4 goes from 1 to 5. So 1 to 5. So that hugs the corners. That goes all the way over here. All right. And again, the idea is where is that element connecting and how does that contribute to the stiffness of the system? Element number 5 goes from 4 to 5. And somebody had said, well, what if we do 5 to 4? What if we do it like this? Okay, well let's follow that element by element. So this element would go here. This element, let's see, 4, 5. 4, 5, that would be there. That would be what? There, or sorry, minus there, and that would be that. And it would be the same answer, so it really wouldn't affect your answer at all. So you would actually contribute the same terms to the global matrix. Okay. Now, element number 6 is 3 to 5. So that goes here. And so there's your 6 stiffness matrices all aligned. And so if you want to assemble, just again, sum each term. So equals the sum of, and then 1 to 1, we're summing that, 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 that. Sum each term 1 to 1. And then take that, copy and paste, boom. There's your stiffness matrix for the entire system. One way, again, that you can check to see whether or not this is correct, ask what is the transpose of this matrix? And is that transpose identical? Well, you could look at it 1 to 1. Sometimes what I'll do is I'll just say, tell you what, tell me what that minus that is. And if I get zeros across the board, then I know that if I take it term by term and I subtract them, I get 0. Well, the only way two numbers subtracted equals 0 is if they're the same. So it's a simple way of checking. Okay, so there's your system level stiffness matrix, and then I went ahead and wrote the displacement vector, or sorry, the force vector and the displacement vector. And again, that just came from the assignment. You were given those. So remember in our last video, we were, quote unquote saying, what's the money? There's the money right there. There's the full-blown system. Okay. All right. So what I'll do is I'll copy and paste this down here. So remember, we're going to delete all these terms because I'm just going to set them equal. I want to make sure I'm using the terms from before. Okay, so I just basically set these terms equal, like that way I wasn't, copying a formula down from below. Okay. So next, so just to go back to the flow chart or to the process, we've written an element level stiffness matrix for each member. We've then assembled that into a global stiffness matrix, or sorry, not global, I need to use the term system level matrix. We've assembled that into a system level matrix for every member. And now I also have a system level force vector, a system level displacement vector. Next comes the boundary conditions. For this problem, nodes 1 and 4 are restrained. So that means I need to knock out rows 1 and 4. So 1 and 4. Again, you're knocking out the ones associated with the reactions. And then columns 1 and 4. So rows 1 and 4 and columns 1 and 4. And then what's left over, you just suck that together, and then that's one reduced system matrix. So it's going to be 3 by 3, right? And so that's going to equal that. It's going to equal that. Equal that. Equal that. And then similarly, we're going to have, let's see, we're going to have this. Give me 1 second. Apologies, I am back. Okay, so we're collecting these terms. So we've got this. Let me set this equal here. Set this equal there. And then set this equal here. Format that. Okay. And then in terms of our codes, this is 2 and 3 and 5. 2, 3, and 5. All right. Okay. And I guess I wrote that in a little bit of a different order, right? Because this is my K matrix. This is going to be the reduced K matrix. This is going to be the reduced force vector. And this is going to be the reduced displacement vector. And so now we've applied our boundary conditions, and so the next thing I need to do is I need to invert the K matrix, multiply it by the force vector in order to obtain these displacements. So maybe what I'll do is copy this down here, and then how do I do that? Well, let's see. So we highlight the region equals, let me move this over. I don't know if the camera is interacting with that. So equals immult inverse of that, sorry, that, close it, comma, that, close it, Control, Shift, Enter. Okay, and so I'll hover here over the formula bar up top, but yeah, I'm just inverting the K matrix, multiplying it by the force vector, and then Control, Shift, Enter, there you go. And so those are my displacements, right? So I've got, displacement at joint 2 is 2.22 inches to the right, joint 3, 0.17 inches, what have you, to the left, and then joint 5, 2.07 inches to the left. Again, positive to the right, negative to the left. Okay, and so the only thing left to do is to form my, big old matrix to determine the reactions and then compute the internal force in each member. Okay, so let's compute the internal force in each member. Okay, so I'm lazy. I'm going to copy and paste all this down here. Move that up a little bit. So here's the my stiffness matrices from before, and so I'd already got that figured out in Excel. So now what I need to do is I basically need to have a set of displacement vectors. So let's color those a little differently. Let's do that. Actually, let me just delete all that and make these green. So here's my stiffness matrices for each element. I then need to form a displacement vector for each element. And so all I do is anytime I see a 1 and a 4, I put a 0 there. So 1, 0, 0, 0, whoop, 0, 0, 0. And then anytime I see a 2, just do that. Anytime I see a 2, do that. Anytime I see a 3, do that. Nope. Anytime I see a 5, do that. Boom. So KD equals F. So now what I do here, let me move this out of the way because I don't want that to interfere too much. So now I've got the K matrix, I've got the D vectors. So now I need the force vectors. Right? So let's, oh, what happened there? Sorry about that. So now what we'll do is we will format these where it's a little easier to see what's going on. Okay, so we have each of our element level stiffness matrices. We have each of our element level displacement vectors. Just multiply them. Boom. There's our force vector for that element, and then I can just copy and paste that to get the force vector in every element. And remember the trick that we used before. We can always use the second number and just look and say, okay, that one has to be 8.89 kips in tension, and for instance, this one has to be 11.1 kips in compression. So there's our displacements at every joint. We have our internal forces in every member. One final step, the reactions. And again, we could assemble these, or we could just go back to the money. Let's go back to the money. Here's the money, and let me set this equal to that. All right, so that's our global level stiffness matrix, and let's see, what was my displacement vector? It was 0, D2, D3, sorry, D2, D3, 0, D5, right? So now we know what those values are, right? D2 is this, D3 is that, and D5 is that. We know what those values are. So because we know what those values are, I can just take the big old K matrix times the big old displacement vector, and what do we get? Well, we get 20, 15, and negative 40 in D2, D3, and D5. We knew those from before, right? So let me drag this down. This is really what I'm after. Let's go back to this. Right? So here's what we were given, right? So what are our displacements? We have 0 at the restrained degrees of freedom, and then we have our known displacements. And as for the force vector, 20, 15, and negative 40, that came from what we were given. And then the R1 and the R4, they're right there. So now we can start summarizing our answer. What is our answer? Okay, so let's look at the answer. Okay, first off, let's look at reactions. Okay, so we know that R1 and R4 What do we know about R1? R1 is 4.75 to the left, and R4 is 9.75 to the right. I actually didn't give you units on this problem, so maybe I should just leave that off. I should just say 4.75 to the left and 9.75 to the right. What about the displacements? So we have D2, D3, D5, right? So D2 is 2.22 to the right, negative, or so this 0.172, 0.17 to the left, and then 2.07 to the left. And then finally, we have our internal member forces. I don't know why I copy and pasted that. And so there are 6 members in this system, so M1, M2, M3, M4, M5, M6. Okay, and so remember, a secret or a quick way of doing that is we can just look at the last number. So this is 8.89 in tension. This is 0.172, 0.17. This next one, here, I'll just move this up here. This next one, the second number is negative, so that's 11.1 compression, 4.14, 20.69, and then 15.17. And then there you go. That's actually it. That's the answer. Now, barring I didn't make any major mistakes during this live recording, that would be the answer to this problem. I'm actually going to check that to see. Let me make sure. I'm looking over here on the other screen. So what did I get? Displacements, right? That's right. Forces, that's right. And then, there you go. So that's the answer. That is the solution to this problem. Hopefully this clarified. I know I went very quickly, but again, as I said, that's the beauty of YouTube. You can always pause and go, wait, what did he do here? And you can always rewind it a little bit. But yeah, and ultimately the matrix computations that you do for this problem are really simple. It's just matrix multiplication and an inverse. Beyond that, it's just the pattern recognition, you know, like what you see here. That's why I like using Excel, because it's very visual and you can see where the terms go. That's all I have. My final video that I'm going to record today, I'm going to talk about the example that we did in class on Wednesday, the truss analysis problem, and I want to show you the matrix multiplication to determine the global stiffness matrix for a truss element. And so we'll work through how that's done. All right, that's all we have. We'll see you in the next video.